Welcome to The Explainer. Isomers can be one of the absolute trickiest topics in organic chemistry. But what if you had a clear strategy, a game plan for every single type of problem? Well, that's exactly what we're doing today. We're going to use real admission test questions to build your personal toolkit for mastering isomerism. Ever been there? You're just staring at a molecular formula, trying to picture all the different ways the atoms can possibly be arranged. It's the kind of problem that can make your head spin, especially when you know the clock is ticking on an exam. But there is a much better way than just guessing and hoping you get lucky. So let's start cracking the code. We're going to break these problems down step by step. And we're not just hunting for answers here, we're learning the thinking process behind them. The goal is that by the end of this, you'll have a powerful set of tools that'll boost your confidence for any exam. Here's our roadmap. We'll kick things off with structural isomers, then move into the geometric puzzle. And after that, we'll master those mirror image molecules. We'll even tackle a really tough challenge question that pulls everything together, and then we'll wrap up with a simple toolkit you can take with you. Okay, first up, structural isomers. Now, these are molecules that have the exact same chemical formula, the same number of atoms of each element, but the atoms themselves are connected in a totally different order. Think of it like having the same set of Lego blocks, but building completely different things with them. Let's zoom in on a specific type called metamerism. The key thing to look for here is a central functional group, like the oxygen atom in an ether. Metamerism is all about the different ways you can arrange the carbon chains on either side of that central point. All right, let's put this into practice. Here's a question straight from a typical exam. We've got 3 options. Now, how do we figure this out without painstakingly drawing every single possible structure? We need a shortcut. And this is where the strategy really shines. Instead of just guessing, we use general formulas. We know the formula for an ether is CnH2n plus 2O, and for a ketone, it's CnH2nO. Now, we just match our options. C4H10O, yep, that fits the ether formula perfectly. What about C488O? That fits the ketone formula, so this means both B and C can show metamerism. It's a great little reminder to always check every single option. Next up is tautomerism. Now, these isomers are kind of cool because they're not static. They exist in this constant state of flux. They're in equilibrium, rapidly flipping back and forth between 2 forms. The classic example, the one you absolutely positively need to know, is keto-enol tautomerism. That's where a molecule shifts between its ketone form and an alcohol-alkene hybrid. So let's apply that right away. Another common question. We've got propanone, propene, and propanol. Which one of these fits that keto-enol pattern we just talked about? The name itself gives us a massive clue. And propanone is our winner. Why? Well, propanone ends in 1, and that suffix is your signal that it's a ketone. And like we just said, that ketone group is the major telltale sign for keto-enol tautomerism. It's the most common example you'll be tested on, so keep your eyes peeled for it.
Okay, let's level up to our next type of isomerism. We're shifting our focus now from just how the atoms are connected to how they're actually arranged in 3D space. This is where we get into what's called geometric or cis-trans isomerism.
Now, there are 2 rules here that are totally non-negotiable. First, you have to have restricted rotation, which almost always means you're looking for a carbon-carbon double bond. Second, each of the 2 carbons in that double bond has to be attached to 2 different groups. If a molecule fails even one of these conditions, it's out of the running. And this slide illustrates that second rule perfectly. Just look at 1,1-dichloroethane. That first carbon is bonded to 2 chlorine atoms. They're identical, so it fails the test. No geometric isomers here. But then look at 1,2-dichloroethane. Each carbon is bonded to 1 hydrogen and 1 chlorine, 2 different groups. It passes with flying colors, and it will have cis and trans isomers. So why does this all matter? Well, here is a fantastic application question. Maleic acid and fumaric acid are geometric isomers of each other. But, as you'll see, their 3D shape has a direct impact on their chemical reactivity. This question is a classic test of whether you really get the difference between cis and trans. The entire answer boils down to one simple idea: proximity. Maleic acid is the cis isomer. That means its 2 reactive carboxylic acid groups are on the same side of the molecule. They're close enough to interact and form an anhydride. Fumaric acid, on the other hand, is the trans isomer. Its groups are on opposite sides, way too far apart to ever react with each other. It's a perfect example of how structure dictates function. All right, let's dive into our third category, optical isomerism. The best way to think about these is to look at your hands. They are perfect mirror images of each other, right? But they are non-superimposable. You can't put your left glove on your right hand. That's exactly what optical isomers are like.
So, your mission, should you choose to accept it when you're faced with an optical isomerism problem, is to hunt for something called a chiral carbon. This is a carbon atom that is bonded to 4 completely different groups. If you can find one of these, you know the molecule is optically active and it will have a mirror image twin. Let's put this into action right now. Take a good look at this molecule. Scan along the carbon chain and analyze what's attached to each one. How many carbons in this chain are bonded to 4 unique groups? The answer is 2. Let's break it down real quick. The second carbon from the left, the one with the OH group, is bonded to a methyl group, a hydrogen, that OH group, and the entire rest of the chain. That's 4 different things. Now look at the third carbon, the one with the chlorine. It's also bonded to 4 unique groups, a methyl group, a hydrogen, the chlorine, and the rest of the chain. So, 2 chiral centers. Okay, you've been training, you've mastered the basics. Now it's time for the final boss battle. We're looking at a question that requires you to combine everything we've talked about. The formula is C2BrClFi. The challenge: what is the total number of possible isomers? Don't let a scary-looking formula intimidate you. You just break it down into simple steps. First, we know it's a 2-carbon structure with a double bond. Now we just have to be systematic. Let's fix the bromine on 1 carbon. We compare it with iodine, which leaves chlorine and fluorine for the other carbon. That's our first structural isomer. Or we could pair bromine with chlorine, or with fluorine. See, that gives us 3 unique structural arrangements. And because each one has different groups on each carbon, they all fit the rules for geometric isomerism. So we take our 3 structural isomers and multiply by 2, for a grand total of 6 isomers. Not so bad when you have a system, right? Whew, okay, we have covered a lot of ground, from structural to geometric to optical isomers. So let's distill all that strategic thinking down into a simple, powerful toolkit that you can take with you into any exam. Here it is, your final takeaway. When you see an isomer or problem, just run through this mental checklist. Does it have a double bond? Boom, check for geometric isomers. Do you see a carbon with 4 different groups attached? Okay, check for optical isomers. Is there a ketone or an ether functional group? Check for metamers or tautomers. And for those really tough ones, just be systematic. This process ensures you cover all your bases and don't miss a thing. See, by approaching isomerism not as a game of memorization, but as a logic puzzle with clear rules and strategies, you can turn that feeling of confusion into confidence. Keep practicing with this methodical approach, and you will be ready for any